Okay. I think we're going. If you want to put your slides.
Right.
Okay. Christian received his master at ETH Zurich under Joseph M. Renz, and now he is a PhD candidate at the Free University of Berlin in Jens Eisner Group. His research focuses on the intersection between quantum information and condensed matter theory. Let us all welcome our speaker.
Thank you very much. Thank you very much for the introduction, and also for the invitation. I am going to present this work about classical shadows using shallow random circuits. And of course, this was joint work between me and all of these nice people. There's Jonas, Marcel, Marius, Jens, of course, and Jakob. So I thought I would start, if I can change slides, yes. I thought I would start with a very high-level introduction about what classical shadows are. And I'm not sure how many or how much you all are familiar already with the formalism. And if you're already very familiar, I apologize. I hope this isn't too boring, but I thought it's good to have a refresher. So classical shadows is a protocol that was introduced by Robert Wang, Richard Jung, and John Preskill in 2020, by which we can take some unknown quantum state rho that we have prepared in some laboratory, and using randomized measurements, we can extract some classical data, which acts as a representation of this quantum state. And what do I mean by representation? I mean that if anybody later is interested in some observable O, by the way, can you see my cursor when I'm pointing at things?
Yes.
Okay, great, thank you. If anybody is interested in some observable later, the classical data on the computer can be used to estimate the expectation value of this observable. And a little bit more in detail, this protocol, as I said, relies on some kind of randomized measurements to extract this classical data. And how does it work? We pick some ensemble of unitary operators that I call curly U, and for now I'm going to be staying vague about what this curly U is, and explain that later. We sample some unitary according to this ensemble. We evolve the state, and then we do a computational basis measurement. And the data that we end up storing is precisely this state where we take the computational basis measurement result and we invert the rotation. Essentially, this is the post-measurement state in the corresponding measurement basis. And this, for the purpose of this talk, is what I'm going to be calling a classical snapshot. We repeat this process some large number of times, and we store our classical data, which is a set of n of these classical snapshots, which together they constitute the so-called classical shadow of rho. And what Huang, Jung, and Preskill showed in their paper is that even a modest size of this classical shadow is enough to predict a lot of quantities related to the states, predict a lot of expectation values. So this is the data that we store, but how do we extract any information from this random data? So the mapping from the state to the classical snapshots is some random process. There's randomness in the choice of unitary, and there's randomness in the measurement result. But on average, we can interpret this as the output of some channel. And the output of the channel is essentially just the classical mixture of all possible output shadows. And each one is weighted by its probability of showing up in the protocol. And so, in a sense, we could think of the data on our computer as a representation, not really of the state, but of the image of the state corresponding to this quantum channel. Since if we just take the empirical average of these classical snapshots, they are all drawn from this probability distribution, we should get an approximation of this M of rho. And this by itself is not very interesting. But what's very interesting is that under the right condition, we can classically invert this channel, which in a sense encodes what the data acquisition process is. By this, I mean that we can literally find some linear inverse of the map and apply it to our snapshots And this gives us some random variables which on average reproduce exactly the state. And if anybody gives us an observable O, it's clear how we get an estimation of the expectation value. We just take the expectation value in each individual ones of these, let's call them inverted snapshots. And by taking the empirical average, we can get a estimation of the expectation value. So in practice, this quantity here represents a shot of some random variable O hat, which is an unbiased estimator of the trace of O row, in the sense that on average, oh, there is a 1 over n missing here, I'm sorry, but on average, this empirical average, for infinitely many samples, this will converge to the actual expectation value. So let's say that we actually want to implement this protocol in practice in some lab. There are a number of prerequisites and things that we must be able to do. So the first step is that from rho, we want to extract this classical shadow. And the very basic prerequisite of this is that we must be able to implement the unitaries from this curly U ensemble that we picked. Of course, if we just want to implement any unitary, even with, say, exponential depth, this will be very hard. So ideally, we want to avoid that. And even then, if we can implement the unitaries, we must be able to store the shadow on a classical computer. Until now, I've said that these snapshots live on the classical computer, and I've been a bit vague about this. But of course, if you remember, this looked like U dagger B. And if U is just any unitary, this in general would be a exponentially large vector. And so in order to even be able to store these snapshots classically, the unitaries need to have some special property. Finally, once we have our shadow, given an observable O, we want to compute these shots of these estimators. And this is all about inverting this channel M, obtaining this classical inverse. And it's not, of course, depending on the ensemble, it's not at all obvious that such an inverse would exist or that we would be able to efficiently apply it using a classical computer. And finally, after we've done all of this work, we have our estimators, and so we can start to estimate the expectation values, which is an unbiased estimator, this O hat, which means that for infinitely many samples, we will get the exact value, but we do not want to take infinitely many samples. And we want to know how large this error epsilon is. And of course, this error scales with the variance of this random variable O hat. And so we're interested in bounding the variance of these estimators in order to know how big this error is. And I think we can divide this in 3 broad categories. The first one is an issue of quantum implementation, and this is the only quantum part of the protocol at all. The rest is all classical post-processing. Point 2 and 3 are issues of computational efficiency. So what our classical computer must be able to do in order to even obtain any estimation efficiently. And the first point is an issue of sample efficiency, meaning if we can obtain estimates, how many samples do we need to take in order to reach some threshold error epsilon? And essentially, there are 3 main variables to play with. Here, there is the state, there is the observable, and there is this curly U ensemble. But we would like ideally not to, from the get-go, have any restrictions on the state and the observables. We would like the protocol ideally to work for the largest possible class of states and observables. And so the only real thing that we're left with is playing with this curly U ensemble. And essentially, the moral goal of many of these shadows works is to find an instance of this curly U ensemble such that these 4 points are as well behaved as possible for the largest possible class of states and observables. Right, and so now I want to dive in a little bit into the original classical shadows protocol as presented by Huang Qing and Preskill and see what they propose as unitary ensembles and what we will highlight a sort of trade-off that is here before moving on to our work. So the first ensemble that is considered in the original classical shadows paper is what is called global shadows. So here the unitaries are drawn, they are all Cliffords, and they are drawn from the completely uniform distribution over the Clifford group. And these are global Cliffords that we apply to our state and then we measure in the computational basis. So the first point, and now I will go point by point and see how these problems are solved in this case. Can we implement unitaries from Carrillo? And this first point is always, of course, this is hardware dependent. There is no universal truth here. It depends on the hardware. But here what we can say is that if we have local control over our qubits, we need order n squared Clifford gates for each snapshot, where n is the system size. And so in linearly deep circuits, and this is of course feasible, but probably outside of the capabilities of current hardware. And this is, I would say, something hard to do with current technology, implementing linearly deep circuits with any accuracy. But as far as storing the shadows go, this is very straightforward. The shadow here is a stabilizer state because it's just a Clifford times some computational basis state, and so here there is no issue at all. We can store this efficiently. Then, once we have our snapshots, we need to obtain the estimators corresponding to an observable, and this is about inverting this M channel. And here I give a little bit of a more precise expression here. You can see here, essentially, this is the average over all possible snapshots. Here we have the average over the unitaries and the average over the measurement results. And here we have the actual snapshots. And in this case, this nice structure of the Clifford group means that there is a simple closed form for this M channel. M is simply a depolarizing channel for some depolarizing strength, which means that there is also simple closed form for the inverse of this channel, and that given some snapshot, computing this estimator is just a matter of computing this overlap here. This is all you have to do, and this is efficiently computable with a caveat for appropriate observables. For example, you might take this O to be a projector onto a stabilizer state, then the overlap with this other stabilizer state would be efficient to compute. And so, but there are observables for which it's not so clear here whether this is computable or not. But for appropriate observables, this is efficiently computable. And finally, we want to use these estimators to compute our expectation value, which involves bounding this variance. And the variance depends on both the state and the observable, but we don't really know the state. The whole point of the protocol is that the state is an unknown. And so what we can do, or like what Wang-Qing and Preskill did, is to maximize our all possible input states to just obtain an observable dependent quantity. And it turns out that the maximum over all states of the variance of our estimators in this global shadows context scales like the Frobenius norm of the observable. And this is extremely good for a kind of global observables, which are low rank observables. And the typical example is if O is just a projector onto some state, then the expectation value in some other state is simply the fidelity between the two states. And the trace of O squared here is 1. And this means that fidelity estimation can be done with a constant number of samples with this protocol, which is amazing. On the other hand, if we were interested in estimating a local observable, this would be bad news, because say that our observable is local to some region A of the lattice and it's the identity everywhere else, there will be here a exponentially large term in the size of this AC. And so in general, we will need exponentially many samples to do this. And this is it for the global shadows. These is all 4 points. And I'm really quickly go through the other ensemble, which is local shadows, which is considered in Wang-Qing and Preskill. And here, instead of drawing a big global Clifford, we draw n independent IID 1-qubit Cliffords, and we apply them individually to each qubit. And so we can say here that 0.1, this is easy. This is just single qubit unitaries. This we can do. 0.2 is the same exact thing. We have the snapshots are stabilizer states, so we can store them with absolutely no issue. Obtaining the estimator is a very similar issue as well to the previous case. Essentially, we have the same thing with the closed form of the measurement channel, except that now it's local. And this is due to Clifford group properties. And finally, we get to the point where everything changes. Now we have that the variance of some k local observables scales exponentially in k, which means that this protocol is very good for local observables, but bad for the global low-rank observables for which the other protocol was so good. So a small summary here is that there are these two ensembles, random local Cliffords and random global Cliffords. One of them is easy to implement, the other one is pretty hard. And the computational efficiency issues are dealt with by the structure of the Clifford group, which allows for closed forms and efficient classical post-processing. And finally, the estimation. Random local Cliffords are very good at estimating local observables. And here I just picked a local Hamiltonian as an example. Say we want to estimate some energy. And random global Cliffords are good at estimating low-rank observables, so fidelities primarily. And the aim of our work is to sort of find a middle ground between these two extremes that are completely local and completely global, find some middle points, which ideally would inherit the good properties from both. And you probably already know or guessed what this middle ground is. The intermediate ensemble that we pick is random circuits. So these are the unitaries that we draw, and each box here is drawn from some unitary to design at least, but in practice we will always pick the Clifford group pretty much. And I say that this is an intermediate ensemble because at depth 0, what I call here depth 0, this is exactly the local Cliffords. And as the depth grows beyond some superlinear threshold, this reproduces the statistics of global Cliffords because it becomes a 3 design. And so we recover the global Clifford scheme. And this is a relatively natural idea as a middle point. And this was also considered in other works by Hu, Achtar, Ayenso, and co-authors around the same time our work came out. In our case, what we examine in detail is the regime where the depth scales logarithmically in the system size. And why logarithmic in particular? Well, as far as the first point goes, this is way easier to implement than global Cliffords, which in general require linearly deep circuits as opposed to logarithmic. And as far as computational efficiency goes, we have a natural framework which is given by tensor networks, and I will talk about this later. And these 2 points are good reasons for picking a depth which is shorter than log, but why should we go all the way to log? A sort of intuitive reasoning that was one of the starting points of this project is that log depth is enough to make circuits anti-concentrate, which loosely means that the output distribution at log depth already sort of looks like the output distribution of totally random global Cliffords. And the hope is that this would reflect into the sample efficiency at the variance bounds, and we would get the same sample efficiency as global Cliffords at much shorter depths. And I will explain later that to some extent this is the case. So, and now for this ensemble of shallow circuits, I will try to go through all of these 4 points and explain how do we solve these problems, and many problems that were easy due to the Clifford group structure will become much more complicated in this case since we lose the group structure. And I will try to explain what we can do, what we cannot do, what we can show, what we cannot show, because there are drawbacks, of course. So as far as the implementation go, I'll use the word feasible here. This is again hardware dependent, but we can say at the very least that this is easier than global Cliffords. And now we move on to I move on to explaining the storage shadows, and I do an extremely brief detour to tensor networks. I'm sure that all of you are familiar with this already. I just want to like get it out of the way and explain the notation as well. So a tensor is simply an object with many legs, and the object we draw as a box, and the legs are the indices. Sorry, it's an object with many indices, and we draw the object as a box and the indices as legs. And tensors, everybody is familiar with, are vectors, which are objects with one index, and matrices, which are objects with two indices. And anything with more than two legs, we just call a tensor. We can contract tensors, which means we connect two of the legs. And this simply means we set the indices to be equal and we sum over them. And the tensor network is simply some arbitrary connection geometry of such tensors. And the most important kind of tensor that I will be talking about is a matrix product state, which is a way of encoding an n-qubit state. So it's a tensor network that looks like this. And if we look at some leg assignment on the top, we can interpret this as vector elements of some states. And since when we fix a leg here, these are objects with two legs, this is just a matrix product, hence the name. And if we look a little bit more in detail at this tensor, this has some upward legs, which is actually the physical leg. This spans indices from 1 to some d, which is a physical dimension. For qubits, this would be 2. And the legs, the lateral legs, these indices span from 1 to some chi, which is called the bond dimension, and this effectively encodes how entangled the state is. And the total number of parameters here is chi squared times d. And so this is a way of efficiently encoding low entanglement states, since if chi is small, this is the total number of parameters that we have to store is also small, and we can efficiently store this on a classical computer. While if we were just to store each individual matrix element, no matter the entanglement, we would always have to store exponentially many parameters. Right, and so the goal was to talk about storing the snapshots. And of course, after I said this, you can guess that we store this as matrix product states. So this is U dagger B, which is essentially the snapshot. U dagger is the unitary that we sampled. B is the measurement result, and it's reversed since it's dagger. And so these bits are inputs to these legs. This circuit can be interpreted as a tensor network, and so this is the actual state that we want to store. And if we look at this path of tensors that I highlighted, and we just isolate this is pretty standard way of converting a circuit into an MPS. We can contract along these legs that are connected here and leave these legs open, and the result will be a box with 3 legs, which is essentially an element of an MPS. And if we do this, if we do the same with all other paths here, we will get an MPS. The physical dimension is 4 because we have 2 qubits here, and the bond dimension is 1 2 qubits leg for every layer here, and there are d-1 layers where d is the depth. Since d is logarithmic in the system size, chi is polynomial in the system size, and so we get an efficient representation for these snapshots. Right. So now we know that we can implement our unitaries that do the measurement result, and we get some snapshots which we can store on the classical computer using tensor networks as this MPS. And now we have a classical computer which is full of the snapshots. What do we do with them? We are interested in estimating some observables, and this requires the classical post-processing. And this is where let's say the more analytically difficult things start, because we lose the group structure. So as a quick reminder, the classical post-processing is all about computing these estimator shots, and in particular inverting this channel M, which is again like the corresponding to the data acquisition step, the superposition of all snapshots weighted by their corresponding probabilities. And just as a quick remark, M is self-adjoint, and so we might as well, instead of computing M-1 of Si, we might as well compute M-1 of O. This changes nothing except it's easier to explain for me. And this will be divided in sort of two main sub-problems. First one is obtain some characterization of this channel M, because since we have no more group structure, there is no more closed form. And once we have obtained this, we need to also invert it, and we will not be able to do it for just any observable. And so the fundamental question is, for what observable can we do it? Can we compute M-1 of O and then compute even this overlap with the snapshot once we have it? Right, so one thing at a time. Let's start by the first point, characterizing the measurement channel. So I said that we have no more group structure. In a sense, we have still a little bit. We still have Pauli invariance. So, which means that the ensembles that we picked is invariant under left and right multiplications by Paulis. And Bu and co-authors proved that this actually implies that the Pauli operators are eigenvectors of this channel. And what is left then for a characterization of this measurement channel is to compute these eigenvalues TP. And for Pauli invariant ensembles, and in particular in our case, we find a sort of explicit expression for these eigenvalues. We show that the eigenvalue corresponding to a Pauli P is the probability that the circuit maps the Pauli to some string containing only identities and sets. And remember that we can always sample these unitaries from the Clifford group without changing the results. So UP U dagger is a Pauli. And actually, we show this is valid for any Pauli invariant ensemble, but in our case for log depth circuits, we show that this can be written as a Pauli n bond dimension tensor network, which gives us complete sort of analytical control over this analytical and numerical control over these eigenvalues, and so over the channel itself. And they want to give some idea of the construction of this Pauli n bond dimension tensor networks. So we want to estimate this probability that the circuit maps a Pauli to a string of identity and Z, and we can start from an easier problem of figuring out the transfer matrix in which we feed a Pauli to some random Clifford and we figure out the probability of getting some other Pauli out. And this is just some 16 by 16 matrix, which we can represent as a 4-leg tensor, where each leg corresponds to a 1-qubit Pauli. And now, if we were to just compose this transfer matrices in the same shape as the original circuit, we would get a huge transfer matrix, which tells us from any input Pauli what is the probability of getting an output Pauli Q. But we are not so interested in this fine grain. We just want to know what is the probability of getting a Z string out. So we just contract with some tensor that keeps I and Z and throws everything else out. And so this tensor network computes this TP. And by the same exact construction as earlier, we can represent this tensor network as an MPS with bond dimension 2 to the D. And so Pauli n if this is log n. Right, so now we have characterized the measurement channel, but this is a completely different issue from actually computing the estimators. Well, it's not completely different, but it's, let's say, it's not enough at all. So let's say that we want to compute some estimators, and let's start from the easiest possible case. Let's assume the observable is a single Pauli. And so in this case, the m-1 of P is simply 1 over this eigenvalue times this Pauli. And so, and this 1 over TP, we can compute it efficiently. And so we can easily obtain an estimator for a single Pauli by just computing this overlap with it, which is efficiently computable, and just divide it by this eigenvalue. And we can slightly generalize this to something that we call a sparse observable, which is simply a linear combination of polynomially many of these Paulis. And a typical example would be a local Hamiltonian, where we would have one local Pauli for each site, for example, of some lattice. And in this case, this straightforwardly generalizes this because we can just compute it by linearity, and this is just polynomially many terms, and we can efficiently compute each individual term, and we get an estimation for these sparse observables. And this is something we can do, and it's a class of observables, but this is far, far, far away from all possible, let's say, interesting observables. There are many observables which are not captured by this. And so we consider a second class of observables, which is sort of natural in our setting, which is observables which are given as tensor networks. So an example would be O to be the projector onto some state psi, where psi has low entanglement. Essentially, psi is an MPS. And yeah, this is sort of a natural thing to consider in the setting, since everything is in terms of tensor networks. And the problem now is, how do we compute this m-1 of O? We can start by a slightly simpler problem, which is how to compute m of O. And we have a tensor network representation for this eigenvalue TP. And essentially, this means that by some basis changes and like by some tensor manipulations, we have a representation for, in terms of tensor networks, for this whole channel M. And so given an observable O, which is given as a tensor network, we can compute M of O just by tensor contractions by using this by using the tensor network representation that we have of this TP, of this eigenvalue. And so the idea is to get some tensor network representation of 1 over TP. And this, okay, this is the problem, right? If we map each Pauli to, if we label each Pauli via some bit string, the eigenvalues of the measurement channel M look like this. It's just some tensor network, and each Pauli corresponds to some upper leg assignment, physical leg assignment. Whoops. Physical leg assignment. And we want to find some other tensor, such that some other MPS, some other tensor network, such that we call it V lambda, such that T lambda times V lambda is always approximately 1. And this is like a much stranger problem that I realized at the beginning. And I do not know, or we do not know, the authors of a way of doing this analytically, or like of an obvious or straightforward way of doing this. And what we can do is to resort to a variational algorithm. We define some cost function, which essentially sums over all possible input bit string. And am I going over time? I hope not. Sums over all possible bit strings the error of this approximate inverse. And this cost function, this is just the picture to say that this we can compute efficiently, given a t and given a v. And we minimize this using a variational technique called cyclic coordinate descent, which means one tensor at a time, essentially. And if you want, afterwards, if you're interested, I can describe this in a little bit more detail. And this is actually guaranteed to converge to a minimum. However, there are many open questions about this. This is guaranteed to converge, but we have no guarantees on the convergent time. And actually, we have no guarantees on the bond dimension required for the cost function to be small, meaning the expected bond dimension of the tensor network of this approximate inverse. And this is what we get in practice when we actually implement this. This is various lines are system sizes, and the different line styles here are different bond dimensions for the ansatz inverse, and we see convergence even for moderately high system sizes. But of course, we would like to obtain rigorous guarantees about this.
Sorry, maybe I missed your point. So how do you guarantee that it will converge to a minima? Is that a theoretical guarantee?
Yes, this is essentially a consequence of previous work about the cyclic coordinate descent method. And in a nutshell, the central realization is that if we consider this function C and we fix every tensor except one, this becomes a function of a single tensor, and this function is convex in this single tensor. And this ensures convergence. Yeah.
Okay. Good. Thank you.
No problem. Right. So now the classical post-processing, we say that this is provably efficient for this class that we call sparse observables. And we have a variation algorithm for this class of shallow observables, but unfortunately we have a few rigorous guarantees about the second point. And with this, I can move on to the final point, which is bounding this variance to figure out, okay, we can now, let's say that we managed to compute estimators for this, for some observable that we're interested in. How many do we actually need in order to be sure that we get some reasonable estimate? And here, just a refresher on what I talked about. Now it's like half an hour ago. On other ensembles, the ensembles considered by Huang-Kyung and Preskill. And in this table, I show how many samples do we need if we want to get some constant accuracy in our estimation as a function of the system size. And as I said before, local observables correspond to, if we want to estimate a local observables, we only need constantly many samples if we have done local shadows. But if we have done global shadows, we will need exponentially many samples in general. And vice versa, if we have a low rank observables and we only have access to local shadows, we will need exponentially many samples. And while if we have access to global shadows, we will only need constantly many samples. And so like you see here that this is sort of two extremes. And importantly, these guarantees, the upper bounds, these hold for any possible states. This is a maximization over all possible states. And so this is just a function of the observable. And in our case, we find that local observables need a polynomial number of samples for any state, while low rank observables, fidelity estimation, needs a constant number of samples, just like global shadows. But importantly, we were able to prove this only for a typical state, meaning that we draw a state at random from a one design, so from some ensemble, and we show that on average the sample complexity is low. This is not to say we know it to be inefficient for any state. Whether or not this is efficient for any state, this is an open problem that I would very much like to see solved. And this involves a complicated computation that I don't know how to do, essentially. But yeah, essentially, whether or not this holds for any state is an open problem. But for typical states, at least on average, we see the same this sort of intermediate ensemble property where we capture both local and low rank observables at the same time, and we also have shorter circuits than the global observables. And the idea of the proof, this is very, very quickly, is to give a lower bound on these eigenvalues at log depth. And we use these techniques where one can map average of quantum circuits to statistical mechanics models, if anybody is familiar with these techniques. Right, and so here we have our complete list. We can implement these unitaries more easily than global Cliffords. We store the shadows using tensor networks. The classical post-processing is doable, and it's relatively easy for some class of observables, and for other class of observables, we can find some heuristic algorithms that do it, but it's hard to find rigorous guarantees. And we can estimate efficiently local observables, and on average, we can estimate efficiently low-rank observables. And finally, I just want to show some numerics where we implemented this protocol for many depths. And so there's like a lot of going on in this plot. The most important part is this blue and green line, which essentially characterize the estimation error as some fixed number of samples. And the left panel, we try to estimate the state fidelity, and the right panel is we try to estimate a local observables. And depth 0 is the local shadows, depth infinity is the global shadows, and we can see that the global shadows are good at estimating the fidelity, but bad at estimating the local observables as expected, and vice versa, the local shadows are good at estimating the local observables, but bad at estimating the fidelity. But we see that as we go towards some short depth, which is non-zero, but still pretty short, we manage to reproduce pretty much the same efficiency as the global shadows, while keeping the local observable efficient, well, at least far more accurate than the global shadows. And so here we can also see this sort of intermediate ensemble proposal that we have. So this, with this I arrive at a conclusion. So we have a middle ground between completely local and completely global shadows. And this inherits good sample complexity properties from both of them, but the cost is somewhat harder classical post-processing. This is, as far as we know, this is not guaranteed to be computationally hard or anything, but it's still like the classical post-processing is much more involved. And we have many other questions. The three important ones I would say is that we don't really have an upper bound on the bond dimension of the inverse measurement channel MPS, which is crucial. And we don't have convergent times guarantees for this variational algorithm. So to know how actually hard is the classical post-processing in the case of shallow observables. And we are missing a variance bound for worst case states for low rank observables. And yes, with this, I thank you for your attention. I hope this was clear, and I will answer questions if you have any.
Thank you very much for the presentation. It was very nice and very well structured. I like that very much. And as our speaker said, does the audience has any questions? Have any questions?
Okay, thank you for the very nice talk. So I have a question. I'm not sure if I understand correctly. I'm wondering, like, you have some part of the circuit and you store them into the tensor network equivalent. So how do I decide which part of the circuit will be stored in the tensor network?
Wait, let me go back to the relevant slide, which I believe is this one, right?
Yes.
So this circuit. We want to store the whole circuit essentially. It's not the whole circuit, but it's just the output state of the circuit of this U-dagger circuit, where the input is the bit string corresponding to the measurement result in the data acquisition process. And we want to store the whole thing. This is some state, and we represent the whole circuit as an MPS. And this is the whole circuit that we apply, and it's a short circuit. It's log depth, which is why this is efficient. Or have I understood your question? Or
so you mean these are the measure results? So this has nothing to do with the original circuit. You just try to store them after measurement, correct?
No, let's say this has to do with the original circuit. If you see the rotation plus measurement plus U-dagger rotation back, you can see this as a measurement in the basis given by U and the computation, U times the computational basis states, this some basis, and you measure in this basis. And what we store here is the post-measurement state. This circuit here, this U-dagger, this is the original circuit that we've drawn from the ensemble, and this we know we have drawn it. And once we have the measurement result, we apply it to this computational basis state, and we get some state U-dagger B, and this is what we want to store. It's essentially not the whole unitary, but a column of the unitary, U dagger B.
Okay, see. So in your intermediate circuit, how do you like go from local to global? So how do you do that? Maybe I missed that part. How do you define them in the circuit? How do you do that?
Yeah, I mean, you mean, I guess, here?
Yeah, I think so.
Right. So these circuits, well, if you just forget everything except the zero, this is just the local. This is just local Cliffords, but a property of these quantum circuits is that the deeper you go with these circuits, the more random they are. And it's been proven, I haven't put a reference here, but this is a famous result of Brandao, Haro, and Horodecki, that if you take this kind of random circuit with completely random gates at each point, and you keep going to some depth which scales linearly in the system size, and you look at output distributions, you will not be able to distinguish this from the completely global Clifford, where you just apply a big Clifford that acts on the whole thing. So these circuits sort of at depth 0, they are local. At depth very long depths, they are global, and somewhere in the middle is the regime that we pick.
Yeah, so maybe my question is how do you apply this random gate or random circuit? I mean, how do you design this random circuit? I mean, do you do the measurement and then apply them later, or how do you design it from the beginning?
So I'm not sure I understand the question. I'm gonna try to answer and let me know if I misunderstood. Each one of these gates is just some. Let's say it's a Clifford. We can always pick it to be a Clifford. So there are algorithms out there where you can just pick a random 2 qubits Clifford from the uniform distribution. You can do classically because you can represent any Clifford efficiently. So you pick a random 2 qubits Clifford, and this, depending on the implementation on the architecture, this you can compile on whatever hardware you have, and you can apply it to the relevant 2 qubits. And so the basic protocol again was that. Wait, where did I? Oh, this is a while back. Right, is that then we apply the unitary we have the state in the lab, we sample all of these qubit Cliffords, applied to the pairs of qubits, just as in the architecture I've shown, the brickwork architecture, and then we do a computational basis measurement, and this is the state that we store. Is this more clear?
Yeah, so basically the state are fixed. So this you don't worry about the Hamiltonian of it behind. Basically, you just try to get the state. So you randomly apply any gate to get the result. This is the spirit, yes. Right?
Yes, essentially, yeah. This is very much something that that you need to do on some controlled computer architecture, where you can just compile gates that you pick in a very controlled fashion. And there are other shadows protocol in which people consider, for example, evolution under Hamiltonians with random parameters, which is more physical in some architecture, but then it's even harder to analyze the classical post-processing, because the farther you go away essentially from these completely random unitaries, the more structure you lose and the harder the analysis becomes, in a sense.
Okay, thank you. So final question. Do you think this can be used in some like VQE circuit? Because usually we are going to estimate some observable, like for estimating the energy or something observable we are interested. So do you think this can be directly applied to this kind of VQE circuit?
Probably. So I don't know so much about VQE. I preface with this, but as far as I understand, probably yes. But the interest of classical shadow is mostly that it's a tomographic protocol, meaning that the usefulness is when you don't know in advance what observable you want to measure, and you want to do one protocol and gather a lot of data, and then later you worry about what observables you have to choose. And I think in VQE you are mainly interested in these energies, and you know already in advance what you want to measure. And so there you might be, and it might be better to do something tailored to this kind of observables.
Okay, I see. Okay, thank you very much. Very nice talk.
Do we have more questions? Perhaps not a straightforward question, and perhaps the answer would be too long, but actually I was kind of curious when you said that you have your results and then you just draw some table and you show that you can do something in constant time, I would say. But this is just for a restricted set of states. It's towards the end.
Sorry, there's a lot of slides. I'm getting there. This one.
Oh, here. Yeah. And you mentioned this this open problem and that you're interested in it. I was wondering if just expand a little bit on what would be needed to find the states, or what's the difficulty that you encountered.
Sure. Yes. Essentially, I can talk a lot about this, so stop me but like essentially what I mean here by a typical state is that, okay, the goal is to compute this variance of the estimator O hat, and this and we want to maximize, or the variance is a function of the observable and a function of the state, and we want to maximize over all states. So we want to be able to say, if somebody chooses the state adversarially, the worst possible state, we want still to have a guarantee. And if you do this, the variance as a function of the state and the observable is a so-called a third moment of the circuit, which means it involves a cubic power of the unitaries in the circuit. While if you average over the states, the variance is linear in the states. And so if you average over the state, this is the same as asking for the variance, the sample complexity, if the state was the maximally mixed state. And so this already intuitively, it's clear that this is probably easier than just any state. The maximally mixed state is probably easier. But what this does in particular is that the variance goes from being a third moment to a second moment. So it becomes quadratic in the unitaries. And for second moments of random circuits, there are these well-established techniques, these statistical mechanics mappings that I alluded to. Essentially, you can map this variance to it becomes the partition function of a model in statistical mechanics, essentially, and which in practice means it becomes a sum of a bunch of terms which are all positive, and they are relatively easy to bound. And so bounding a sum of positive terms is relatively straightforward, just forget some of the terms. And so we can get an upper bound to this relatively straightforwardly. While if you go to the third moments, so if you want to really maximize over all states, you can still apply the same techniques, but essentially the computation becomes a huge mess because you get negative terms, and it's very hard to figure out how to get rid of the negative terms, etc., etc. And I would have to show pictures and go a little bit into the details to show where the problem really is. But essentially, the heart of the issue is computing a third moment of a random quantum circuit, which, to the best of my knowledge, is something that analytically there is no real control of at the moment, as opposed to second moments.
Oh, I see.
The technique that we use is essentially.
It does remind me of a paper that I saw a long time ago. Oh, sorry, please.
No, please go on. Please go on. What paper?
It's because when you start mentioning like the second and third moments, I kind of remember that there's like a huge paper. I think perhaps David Gross is one of the authors, and I remember that they derived several results involved like just computing like this sort of functions. But I also imagine that perhaps you know about this. I'm not sure if this could help at all.
From this description, I cannot identify this paper, but yeah, I mean there is a lot of literature on.
It's a little bit vague. Yeah.
There is a lot of literature on computing these kind of things, and this is like computing moments of how random unitaries is relatively it's a relatively solved problem, but the problem is the geometry here. Is that the only real like essentially the reason why you have all of these nice closed forms in the global Clifford's case is that you just have one big unitary, right? And computing these moments for this case is doable. It's a very well established theory. But the only thing you can recover in this case is that locally you compute this average here, and you have to essentially figure out how each average interacts with the average above and below, in a sense. And this becomes, from here you can see where the statistical mechanics things come from. It becomes a sort of 2D lattice, right? And in this random circuit case, this becomes untractable very quickly.
Okay.
And
all right.
Actually, a lot of these shadows were like this shortcut somehow that we took of having a typical state as opposed to the worst case state. This is something that, unfortunately, due to the hardness of the problem, has become sort of standard in these works, where unfortunately we cannot say anything for the worst case, but we can say something on average if we don't have enough structure.
Okay. Okay. Thank you very much for expanding a little more on that. I'm not sure if the audience has any other questions. I would think that this is a no. So let me thank you again for accepting coming here and for the very nice talk. And let me stop the recording.
All right.